Welcome to our 6th video, in which we'll be looking at intersections of a line and a plane, intersection of two lines. Intersection of two planes we might do in another video. Well, one of the most common applications of the intersection of a line and a plane is when you have to find the distance between a point and a plane. So it's easy to figure out that if we have a point here, A, minus 1, 1, 1, and we want to know the distance from the point to the plane, we would need to measure in a perpendicular direction. And luckily, that's given to us by the Cartesian equation of the plane. In fact, we can write the equation of this line connecting the point with the plane to give the shortest distance using a fixed point and a direction vector. Pause for a second and fill in what those elements are. Yeah. So the equation of this line joining the point to the plane in the shortest distance, we'd have the point A as the fixed point and the normal vector of the plane as the direction. Now this gives us the parametric equations for x, y, and z. And if they meet the plane, then they must satisfy the equation of the plane. So if we replace x, y, and z in here, it's got to equal 2. And therefore we can find the value of lambda. And in doing so, we can calculate the coordinate of where this line meets the plane, 0, 2, 1, and therefore calculate the distance. I'm going to leave you to finish that. Think about it. It's example 45 in the book. And that's really the basic procedure of finding the intersection between a line and a plane. You can find the x, y, and z coordinates in terms of the parameter and replace them in the equation of the plane. Now, parallel, skew, or intersecting lines. Well, we've all seen vapor trails like this. Those are pretty much parallel, aren't they? But we've also looked up at the sky and seen vapor trails like this. And from below, they may look like they're intersecting. Of course, that's not ideal. That's why we have air traffic control. These are actually skew. They're going in different directions at different altitudes. They're not intersecting at all. So when we're given equations of lines, we may be asked, are these lines parallel, skew, or intersecting? Well, this one's kind of done for you. Show these lines are parallel. So we're given the parametric forms. If we write it in the vector form, why does this mean they're parallel? Ah, there's the answer. Because this direction vector is a scalar multiple of this one, then the lines are parallel. Actually, I just remembered, to show they're strictly parallel, you would have to show that this point is not on this line. But we'll do that another day. If you were to enter those two equations in your calculator and ask it to solve, it will tell you there's no solution found. That's because they're parallel. So, if we look at these three systems, are lines 2 and 3 parallel, intersecting, or skew? Let's look at the equations. We can see straight away they're not parallel because these direction vectors are not scalar multiples of each other. Now we can find if they're intersecting. And the way we do that is to set up the parametric equations for each and then set them equal to each other. Because if these lines intersect, then that means there must be a moment where the x, y, and z coordinates are all equal. So we can set up this system. The easiest way to solve that system is to take a pair of the equations, solve them simultaneously for u and t, and then replace those values in the final equation and see if it works. And it does. So we found u equals 1, t equals minus 2 satisfy all three of these equations simultaneously. Therefore, these lines do intersect. I think I've got that example here, haven't I? Yeah, here it is. Okay, so here are the two lines. They kind of look like they intersect, but I'd need to zoom out to convince myself. There's the two lines intersecting, and we calculated 3 minus 2, 7. 3 minus 2, 7. There's the point of intersection, right there. Okay. Then the other pair, lines 1 and 3, are they parallel, intersecting, or skew? So again, you can look at the direction vectors 2 minus 2, 4, 2 minus 1, 3. They're clearly not parallel. Are they parallel? Sorry, are they intersecting or skew? Pause for a moment to set up the system and solve it. See what happens. Pause the video. Okay, you should have this. If we take any pair of equations for x, y, what did I choose here? Yeah, x and y. Solve them simultaneously. You can solve that for u and s. Replacing the third equation, it's not balanced. That tells you these equations are skew. So if I go back to my figure and add in that third line, which is 1 minus 1, 4, 2 minus 1, 3. Okay. Oh no, I did the same one again. Oh yeah. I think it's the first one. Yeah. Minus 1, 1, 1, 2, minus 2, 4. If you focus on the purple line and the green line, those are what we mean by skew lines. See the purple line and the green line from certain perspective, like the vapor trails, they look like they're intersecting. But you can see from another perspective, they're not going to meet. They are skew lines. If I zoom out, you can see the first pair of lines meet where we calculated they'd meet, right there. But the second pair we analysed are going in different directions. They're never going to meet. Those are skew lines. Okay, after this we'll do intersection of two planes.